Hello! In this video clip, we're going to explore the concept of center of gravity in physics. We'll first review what center of gravity is, how it's related to center of mass, torques and forces, and most importantly, translational motion and rotational motion. We'll see how equilibrium involves applying center of gravity principles, and we'll look at instability and stability of structures and objects using center of gravity, and we'll see how it's applied in body positions and sports maneuvers, the safety of aircraft, and the design of race cars, and so much more. So we'll try to get a handle on the center of gravity of basic geometric objects and look at how to do it for some other unknown geometries, and how to apply that to a lot of problem solving. So this is intended for some college physics students to apply to some of their lab work, and in other problem solving areas they need center of gravity. So stay centered while we weave in some video demos with these slides. Okay, so let's review what center of gravity is. Short, we use CG, or some books might use COG. And it's the approximate point where all the weight is concentrated, where all the force of gravity will approximately act on that object. Okay, so center of gravity is going to depend on a few different situations. When we think of a rigid body where all the points move with the same velocity, the center of gravity will depend upon the geometry of the object and how the mass is distributed. Okay, so what we want to do is connect center of gravity to center of mass. Every object has a center of mass. So if you take an object like a brick and we assume that all the mass is distributed evenly throughout that brick, we could say the center of mass is in the center of that brick. And if we put that brick in a gravitational field where the gravity it feels is the same on all points, then the center of gravity will be exactly the same as the center of mass. Okay, so center of gravity points will coincide where the center of mass is in a uniform gravitational field. Where you get into trouble is when you put that body in a gravitational field where the acceleration due to gravity is not constant on all parts of that object. Okay, so what happens is the torque at the center of gravity should theoretically be zero if it were to rotate about that point. Okay, so many problems we like to align that center of gravity with the axis rotation to make the problem solving a little easier, and of course that just depends on the problem. So in general, we could say the force of gravity, or the weight at the center of gravity point, okay, so the weight at the center of gravity is going to be the mass, the center of mass value, times the acceleration due to gravity. So for us on Earth, that's about 9.8 meters per second squared. All right, so let's take a look at center of gravity in equilibrium situations. So I've put up a standard problem shown in the diagram here. And what we want to do is review our conditions for equilibrium and see how center of gravity is applied here. So the conditions for equilibrium are that all our up forces, our translational forces, sum to zero, okay, and that all our torques, all our forces applied off at a certain position with respect to a rotation axis, are summed to zero as well. So torque is the cross product of your position R cross F, where the force is applied. And when you look at this ruler, this object for which we want to look at the equilibrium conditions for, you'll see that you have four forces acting on it. You have the weight from the ruler, and the weight from the ruler will be concentrated at this point. So we could average it out to this center of gravity point. So we could think of the ruler as uniformly distributed with mass, and the weight of that ruler will act through the center, through its center of mass. So the weight through the CG, the ruler, the center of gravity, will be through its center, and it's going to go downward. Now this will be opposed by this contact force of the stand that it's on, so it will provide an upward force. Okay, and we also have two other forces. We have a mass on the left that's put on this ruler, and it will create a weight due to that mass, a weight force acting down on the left. And to put this object, this ruler, in equilibrium, I use my finger to apply a force just enough to put it in the static equilibrium state where it's totally at rest. So I have 3 downward forces and 1 upward force here. So all those would add up to 0 using Newton's second law. The sum of all your forces equals the mass times the acceleration, or is proportional to the acceleration. Now the torques here, the torque vanishes at the center of gravity, just as mentioned in the last slide. Okay, now the reason for that is I'm assuming, or I'm creating my axis rotation through the center of the ruler, right through that center. So the center of gravity weight is going to vanish, and the force from the pivot back on the ruler is going to vanish. At that point, my R value is 0. Okay, so remember, torque is the cross product of R cross F, and it operates in this third dimension, R being your position of which the force is applied. Okay, so in this case, I have 2 non-zero torques that are acting on this ruler. So I get a torque from the mass on the left right here. So its torque will be its position with respect to the rotation axis. So that position is all the way across here. Okay, that's your R value. And the force will be the weight acting down. So that's in the second dimension. And the torque will be that third direction from the cross product R cross F. Okay, so that's going to create, if itself was acting on, if the weight from the mass was only acting on this ruler, it would create this counterclockwise motion from the torque. Now my finger is going to counteract that with another torque. And as you can see, you have what's called the moment arm, which is the R value, the position with respect to the axis rotation. So my finger is going to act along this moment arm. Okay, it's going to be a certain position, and it's going to act downward. It's going to apply a downward force that would create alone a clockwise motion. Okay, the torque will be in a clockwise motion. And now what we call this line of action is where we apply the force. So the line of action is where you're applying the force, and that line of action will always be perpendicular to your lever arm. So some important ideas here. Now, the torque from this mass will be counteracted by the torque from my finger, and they will sum to 0. So that produces a rotational equilibrium. Okay, so again, in some problems you could adjust the axis rotation depending upon what you have and what you know and don't know in the problem. But in many cases, we like to have that axis rotation right through the center of gravity point. All right. Here's an interesting way of balancing out center of gravity and making something like a bottle being in equilibrium based on the positioning of its center of gravity over this base of support that you see here. So here we have the center of gravity, which is about the average for this type of bottle. Around the center right here, and you could see that this center of gravity is positioned above this base of support right here. Okay, and this base of support is pretty narrow. We'll see the wider base of support you have, the better balance and stability an object will have. So you always want to have that center of gravity above this base of support, and this allows it to be in the state of equilibrium. Now, if you're going to do a problem here and look at the net forces and the equilibrium conditions, you would say that the upward force of the support is going to be balanced by this center of gravity downward force. Now, this upward force is provided by this wood piece onto the surface it's resting on. So here's a problem you can work on. And you could see that other bottle holders are not necessarily just diagonal like this, but we have curved ones as well. All right, center of gravity and stable equilibrium. So what makes some bodies in stable equilibrium or systems? Well, that really works on several properties. One big property here is when we look at where the center of gravity is positioned with respect to where it's pivoted. Okay, so a typical banana, you could see it's curved like this, and it has a center of gravity just outside the banana. Okay, if we approximated all the weight. So if I place a banana and curve it downwards on my finger, I'm using an upward force to balance it out. It's downward weight center of gravity, weight due to the center of gravity. Now, the center of gravity is below the actual pivot point. So this means it's in a stable state of equilibrium, and any little disturbance, so if I tap it on either side, you'll see that it'll wobble back and forth a little bit. And you could try this. And it's got this restoring torque that tries to get it back to this equilibrium position. So that's how you can think of something that's in stable equilibrium. Okay, and we'll look at some other situations that create stable equilibrium. So just like that banana, we could see the same idea with boomerangs, bouncing birds, and some other center of gravity demos. So this boomerang right here has a center of gravity that is just below its pivot point. So here's the center of gravity, and here's where it's pivoted. Okay, and that provides a stable equilibrium. So you could tap one in and it wobbles back and forth about that equilibrium position, that center of gravity to put itself back into equilibrium. And the same goes with these bouncing birds right here, right? So the center of gravity is just below the tip of the beak, and each of these wings are weighted. So if I tap on one of these wings, it wobbles back and forth. I apply a torque, a force at a certain position from the axis of rotation. It wobbles back and forth, back and forth. All right, so that provides you some other examples of stable equilibrium. Unstable equilibrium. So if you've ever played with Jenga blocks or some of the other types of puzzles out there, like this stack right here, which has a rounded base of support, you might encounter unstable equilibrium. So here we have the center of gravity lies outside the base of support. And if you could take that center of gravity and you go over the base of support, like in a leaning tree, a leaning tower, what's going to happen is you become very unstable, and it's just a matter of time before it tips over. Okay, so any small displacement from this equilibrium will cause the object to rotate further away from the equilibrium due to these torques and these forces. So the Leaning Tower of Pisa is a great example of this, right? So if I take this house shown at left right here and I were able to tip it over so much more, eventually that base of support right here will not provide it the stability it needs to stay upright. And here again with this puzzle, the rounded nature of the bottom contributes to its instability. All right, so let's look at center of gravity and unstable equilibrium. Good example is stacking bricks. If we stack one brick on top of the other and have some overhang, we will see at some point it becomes so unstable it topples over. Well, where is that point? How can we determine where it will become unstable? Well, that has to do with where the center of gravity is positioned with respect to the stack and how many bricks you have, and with respect to the base of support. So here I have this bottom brick, which is my base of support, and if I stack one brick on top of another, here I'm doing 2 centimeters, and you'll see this in our video demo, and I assume the center mass of each brick is in the center. What I'll see is that the center of gravity is somewhere in the middle here, and at the point where that center of gravity becomes over that edge of support over your base of support, that's where it becomes unstable. So if I were to stack one more on here, it will topple over, or it'll get very close to toppling over. I'm testing my luck there. So there's other things that play a role in the stability, such as the friction between the bricks, how they're uniformly distributed with respect to the mass, etc. Okay, you could also try this with uniform wooden blocks like Jenga blocks, and you could try different structures. So anybody that's played Jenga is familiar with this. And you could figure out how many bricks you could stack with respect to how much each overhang is in this problem using your center of mass principles. And here's your basic formula right here, where n is the number of bricks or blocks that you stack. Now, there is an interesting problem that is presented with this idea, in that you could theoretically stack infinite amount of blocks or bricks as long as the overhang is the harmonic series. So it gets smaller and smaller as you get to your base of support. And theoretically, that would be an infinite amount. It's just that your base of support will be so much the same. It's really hard to get those infinitesimally small overhangs in that case. So a very good problem to look at. Hey there, folks. With me is Dr. Seth, exploring center of gravity and unstable equilibrium. So what we have here is a stack of bricks, and we're going to start with this base brick, which Seth is going to measure to be how long?
About 19
centimeters. So what's half of 19?
8. Wait. 9.5.
That's correct. And if we assume that these bricks are uniformly distributed with mass, there's a uniform distribution of mass, we'll assume that the center of mass is through the center of the brick. And since it's in a uniform gravitational field, the acceleration is pretty much the same for all parts of the brick. We will say that this center of gravity coincides with the center of mass, which is right through the center, about 9.5 centimeters. So what we want to try to figure out is about how many bricks we could stack 2 centimeters from the edge of the previous brick before it is an unstable equilibrium and topples over due to the torque of its displacement. So how many bricks do you think it'll take before this topples over? Any guesses, Dr. Seth?
Maybe 6.
Maybe 6. Okay, let's see. So we're going to measure about 2 centimeters from each brick. Let's see here. Close enough. And let's put on brick number 3, about 2 centimeters. Now what you see here is this is your base of support right here. And where you run into unstable situations is when you're over the bottom base. Okay, so let's see here. So now we're about 4 centimeters out, and we're going to do another one. Okay, we have 4 bricks, so we have a total of 2 centimeters, 2 centimeters, 2 centimeters, 6 centimeters. So we're not quite at the 9.5 point. Let's see. Or over the base of the brick. Let's try a few more.
Oh, it's starting to shake.
Okay, let's try another one. That's 5 bricks.
Which is 10 centimeters.
And 2, 2, 2, 2. So we're not going to count the bottom bricks. So we're with 6 bricks, we're at 10 centimeters. Okay, can we push this over?
Close enough.
Okay, so we're over the halfway point, but you could see, okay, real careful here, the center of mass here for this top brick. We're going to assume all the center of masses are in the center of each brick, the center of gravity.
My count is
So
off.
this center of gravity goes all the way down. So we're pretty unstable here.
We're over 30 centimeters tall right now.
Okay. So we're pressing our luck here. If these were nice uniform bricks. Oh my goodness. There we go. Too unstable. Once that top brick was past the base support and the center of gravity was beyond the base, well, there's going to be a displacement torque that will result in this toppling. Unstable equilibrium due to center of gravity. All right, thank you. Mr. Seth, take a bow for science. Yay! So as you can see, center of gravity really relies on positioning, and we can see this with the human body. So most people have a center of gravity that's close to the waist. So women tend to have it a little lower down in their bodies. Men tend to have it higher up, and so do children. So we could change that center of gravity just by raising our arms in the air where you're hiring your center of gravity, or arching down as shown in this diagram. So your center of gravity and positioning really affects your balance, as you'll see in some upcoming video demonstrations. Now, center of gravity and using it to take down an opponent, such as in a wrestling match or in a karate match, relies on trying to get that person's center of gravity off their base of support. You want to get them leaning, just like that leaning building or a leaning stack of bricks. So if we could take these arms and shift the legs so that the base of support is not underneath this person's center of gravity, we could take them down. So there's a lot of application there.
Okay, so next I'd like to use the principles of torque to help understand how to use good technique flipping someone in judo. And so here on the left we have an illustration of good technique on the left. We have a flipper, which is the person on the right with the dark hair, and he's applying a force to the opponent, the flippee, which is on the left. And so we can see that force on the right through that lever arm. And so what that flipper has done is he's found the pivot point as close as possible to the opponent's center of mass, so that the opponent's center of mass does not generate a counter-opposing torque. And so that makes the torque basically just a clockwise torque with almost zero counterclockwise torque. And so the person flips easily and feels light as a feather. Now on the right, we have the flipper still applying the same force through the same lever arm distance, but now the pivot point is far away from the opponent's center of gravity, which is that red dot that you see there. And so that gives rise to a large counter-opposing torque because of the large perpendicular lever arm distance from the pivot point to the weight vector which goes through the opponent's center of mass. And so he says that as he tries to flip that same person with poor technique, you weigh a ton, but they obviously weighs the same in both situations. And it's good technique in the left-hand situation. So that's a black belt technique. On the right, we have a white belt technique. Okay, so let's try this then with Mrs. Call.
We'll do some theory in action. Now, the question is, can he flip me? All right,
Okay. So what we're going to do then is I'm going to try to find her center of gravity, and I'm going to get as close as possible with my hip to her center of gravity position, and then we'll pivot about that position. And we can see that she is light as a feather. It was easy to flip her. There was no counter-opposing torque, and she's a very good sport.
Dr. E.
That was not too bad. That was, I'm surprised. Yeah, that was very good.
Was that What's that?
Try again.
Okay, do you want to try again? Okay.
Sure.
All right, now the question is, can I keep Dr. E's counter torque at bay and flip him? I think I got it. Good theory.
Good job.
Now it's in practice.
Yeah.
Whatever. And of course, in gymnastics, we apply all kinds of center of gravity. So acrobats doing flips and any kinds of rotations in the air, like with figure skaters and so on, really relies on how you apply your force to get off the ground and how you use that center of gravity for your rotations. So when you're doing a flip, you really have to, you can't stand in a straight line and have your center of gravity lined up. You have to have some sort of tilt to start, and then you want to launch off with some power and then have that center of gravity in a position that you could rotate about, because once you launch off, your trajectory is going to be around that center of gravity. So some important applications of center of gravity there. So here we are, and with Dr. E to explain some torque and center of gravity.
All right, I wanted to look at some practical applications of torque, and one of them, which I think is perhaps something that we can all relate to, is just simply walking. You know, this is something that seems kind of easy to do, automatic, I would say, but not if you're a baby. If you're a baby, your center of gravity is tipping all over the place, and you just feel horrible for these poor little darlings as they fall and they catch themselves with the corner of the coffee table on their forehead. But they've got to learn, right? And so what is going on here? Well, your center of gravity is where we can imagine all of your mass to be for these kind of problems. So what you need to do is keep your center of gravity between the pivot points. Now the pivot points, in this case, are your feet. And so what we would say then is that I'm very unstable this way because the pivot point would go between my toe and my heel. So my center of gravity has to be between my toe and my heel, or else I'm going to generate a torque because my center of gravity will go past the pivot point. So we can see that here on the board, looking at me from a side view. If my center of gravity, here's my big feet, goes this way or that way, by just a little tiny bit, I get over to this position. Then here's my lever arm, here's MG, and then this becomes the pivot point. And so I start to fall sideways, either this way or that way, or from the front, I fall this way, or from the back, I fall that way, as that center of gravity goes past the pivot point. Now you're going to be more stable to sideways motions. So if you're perturbed this way, then these are the pivot points. And so there's going to be greater stability because you go all the way to here, and you're still not quite past this pivot point. And so I can go all the way to here and I'm okay. I can go all the way to here and I'm okay. But if I go just this far back, just a little tiny bit back, just a little tiny bit forward, I start to fall over because my center of gravity has crossed over the pivot point. Now what about if I'm getting out of a chair? Well, if I'm getting out of a chair, there's a right way and a wrong way to do this. The wrong way is to have my feet out here and then try to get out of the chair. It's not working. Go, okay, you idiot, you've got to pull your feet back in like this, and then you can lean forward. So now what's happening? As I lean forward, my center of gravity goes past the pivot point, generates a clockwise torque, brings me up to a standing position. Okay, so here I am leaning forward. Here's the chair. But I pulled my feet back in like this until my center of gravity gets past the pivot point. Then that generates a lever arm, and that produces a clockwise torque, which brings me to an upright position, but then I've got to maintain my center of gravity between the pivot points of either my toe or my heel in this direction, and between my 2 feet in this direction. But if I have my feet way out here like this in the chair, then no matter how far I lean forward, I'm still going to have a counterclockwise torque, which prevents me from going into the upright position. And so that's what happens then when my feet are out here like this. I mean, I could even give it a really good try, and it's not going to happen. Now, in Calico Ghost Town, near Barstow, California, they have a room that looks level, but it's not. You're actually on an incline. And then they have you sit in a chair. It looks like the floor is level because of vanishing perspective. They have the thing set up so that you psychologically think the room is level, but then you see water flowing uphill, which you know can't be right. And then they ask you to get out of the chair. And you can't do it. They go, well, we'll give you $10,000 if you can get out of the chair. Can't do it because my center of gravity can never get past the pivot point, even for $10,000. Now, if I had a lead hat, that might be a different story. But then it would cost a lot of money to make the lead hat, probably more than $10,000. And then I'd have chiropractic bills as well, because my neck would not be in good shape. But we can see what's happening there in that situation, because here we've got the chair on the incline, and then no matter how far you pull your feet in, as you lean forward, you can never get past that pivot point. So this is your center of gravity here, and that center of gravity can never get past your pivot point, which means that you can never stand up on that kind of an inclined surface without using your hands to aid you. Okay, now what about if somebody tells you that you need to pick that thing up, and I'll give you $100 if you can pick it up, but you have to keep your back up against the wall while you do it. So then I go, okay, well, no, it's just not working, because the farther out my center of gravity goes, eventually I get past the pivot point, which are my toes. Okay, and so then what I feel is my tension the muscular contraction of my toes. I'm trying to push up as hard as I can, but it's not enough, so I fall over. So the only way that I could do this is by maintaining my center of gravity between these pivot points, which I can do by kneeling down. And then I can reach out. That pulls my center of gravity out a little bit, but not past these pivot points. So that now I can pick this thing up. These are concepts then that we have grown to think of as being kind of automatic, but they are all based on very sound principles of torque.
Thank you, Dr. E. Okay, pose number 1 with a center of gravity over his base of support more. Okay, now if he puts his arms back and changes his center of gravity, let's go ahead and see how that change in center of gravity works. Oh, what a finish. What do you think, Sky? Now we have a older boy in the mix here, and we're going to look at his center of gravity. Okay, and typically, again, men have center of gravities higher up in their bodies than women do, and so do children. So here we have a teenager. He's 13, and we'll see if he can topple this up with his nose, his toy rocket, and he's able to do that with his elbows touching his knees so that his center of gravity is over his base of support. Now what we're going to do is we're going to put his Let's go ahead and put it back in the same position. We're going to put his hands behind his back and change his center of gravity. And let's see you try to topple it over without moving. All right. Hey there. Now we're going to try my center of gravity and see how it differs from the two previous contestants. Okay, I'm going to try to topple this rocket over with my nose. No problem. My center of gravity must be over my base of support. Okay, but now if I go ahead and put the rocket in the same position and I put my hands behind my back so I change my center of gravity, can I do it? Yes, just barely without toppling over. So I must have a lower center of gravity than the two previous contestants. This is something you could try with all your family members and see who could have that stability, that equilibrium. All right, thank you. So, center of gravity has a lot to do with the shapes and the geometry of the object. So if you have uniform mass distribution, usually you can intuitively see where that center of mass, that center of gravity will act. Okay, so the center of mass, center of gravity of this triangular boomerang is going to be right in the center. Okay, so we can approximate that as being where the weight force will act, and the same with this ring, and the same with this cardboard, this square cardboard piece. All right, so how do you find the center of gravity of some other interesting geometries? So here we have a pathological one shown in this diagram. And to find its center of gravity, we could apply this clever technique, which involves hanging it by some of its edges and drawing a line down, straight down, showing where the gravity is acting. So if we draw a line down by hanging it off this edge, and then I draw another line down by hanging it off another edge right here, I draw a line down, I would see where the intersection of those lines are, and that would be my center of gravity. So to be more precise with it, we could take a mass like this, and we could hang it down from the edge, so that makes a line, and then we would draw another line by hanging it off this edge. Okay, and we would get an intersectional lines. You could do a third and double check that. You could do a fourth, and so on. And eventually you get this point of intersection, voila, which is where its center of gravity is. So anyways, that's a great trick you could apply. And when it's not uniform mass, well, then we have this nice triple integral that involves the density in 3 dimensions. So you could try to attempt that in your problem solving of the more challenging center of gravity problems. All right, and of course with cars and vehicles, center of gravity becomes really important, especially in safety or in trying to get cars to do tilting maneuvers and bank higher curves, steeper curves, etc. So race cars tend to have low center of gravity so that they don't tip over, and they could use that to make a lot of maneuvers. And we know the more boxy the car or vehicle is, like a garbage truck or a Jeep, there is more tilting and instability associated with it because it has a higher center of gravity. Now, center of gravity becomes huge in the safety of aircraft. Okay, so airplanes have a center of gravity that's dependent upon the body of the plane, the wings of the plane, the engine, the tail, the payload, and the fuel. And what we do is we take all those weights and we average those weights from a certain point, the center of gravity point of the aircraft, and we have a certain bar of room where that center of gravity operates, right? And we don't want that to change too much because it affects the rotation of the airplane, because it will tend to rotate about its center of gravity when it's in flight. So this also plays a role in rockets and how they roll about when they take off and are in flight. So typically what we do is we say the center of gravity will be at a certain position, and we take the weight at each part times each position. We sum those up to get the total. And when we're looking at aircraft, we have to look at all the up and down forces. So we have the weight of the aircraft. So if we approximate it at center of gravity, that would be the weight at the center of gravity point will be counteracted by the lift. And then what we have is we have the thrust of the airplane going forward, and then we have any drag pointed in the opposite direction. So here we definitely want to make sure the sum of our forces, translational forces, sum to 0, and that all our torques, we want to avoid as much torque, external forces applied at positions from your axis of rotation. We want those to be summed as close to 0 as possible, okay, to make a stable ride on an airplane. Now, center of gravity becomes a little bit more challenging when we're looking at astronomical bodies. And the reason is now we're starting to get away from a uniform gravitational field. The acceleration due to gravity, little g, is not always 9.8 meters per second squared. So that changes. So we start really looking at center of mass more and the rotation about the center of mass, which can change. So when you look at the Earth-Moon orbital mechanics and rotations, the center of mass of the Earth-Moon system is just below the surface of the Earth. So both the Earth and the Moon fall about that center of mass. Now that center of gravity is going to be different because the Moon and Earth are going to be at different positions. Sometimes they're closer together, sometimes further apart. So that's not a uniform gravitational field. So the center of gravity doesn't always coincide with the center of mass. And the same with the Earth-Moon system going around the sun. Okay, so sometimes it'll be closer, sometimes be further away. So that acceleration or that gravitational field will be changeable, will be changing. So what we want to do is approximate where the center of mass is. The approximate center of mass between the Earth, Moon, and Sun system is, again, just below the sun's surface there, because the sun is extremely massive. So if you average out all those masses, you'll see that the middle mass part is just on the surface of the sun. And of course, center of gravity plays a huge role in trees, these structures and so many other structures. We know that tree has to be balanced. So if all the limbs are not balanced, it will easily tip over. And a lot of times we'll get burn scars from fires that affect the weight distribution of a tree and can affect which way it'll fall over. Okay, so here's some giant sequoias, and there's a lot of weight on these. They're massive trees, and they want to balance out that center of gravity with the distribution of all parts of the trees. So we'll show you some video clips coming up. Hello there, folks. With me is Mrs. Sky, my 2-year-old little pocket beagle, who's going to help us demonstrate some doggy center of gravity. And as you can see, she's on all fours right now, and her center of gravity sort of coincides with the middle of her body coming down, giving her a nice equilibrium balance. Her center of gravity is over her base of support. She has a very wide base of support, which keeps her in stable equilibrium position as she's on fours. However, if we change her center of gravity by, let's say, holding on to one paw, lifting one paw, or lifting the other paw, her center of gravity shifts. And of course, she's very good at balancing out her hind legs, balancing on her hind legs, and being in an equilibrium state. Let's go ahead and see how much of a equilibrium pose you can produce, Miss Sky. Can you show us your center of gravity shift when you are on your hind legs? Oh, good girl. She's very good at balancing out on her hind legs. Okay, let's see you do that again. So as she moves up and balances out on her hind legs, come on, up, up. Come here. Come here. Her center of gravity shifts. Oh, she's trying to get a little bit of stability by falling on me. Let's see you just do it all by yourself. So right now her center of gravity is over her base of support, her hind legs, and she's able to be in a state of equilibrium. The moment her center of gravity shifts off her base of support, she will experience a displacing torque and topple over. Let's do another good one. Oh, good girl. Come on, you can get it. Good girl, good balance. All right, that's Mrs. Sky CG signing off.